Well, today we're going to explore chemistry, and our guide is Dr. Iona Black. Professor Black is a much beloved professor at Yale University in the chemistry department, and shortly you'll see why. Now, some cool things about her. She's going to tell you about the science, but I'm going to tell you what I think, why she's so cool. First of all, her hometown is New Jersey, which is the home state is New Jersey, which is mine as well. So that's why. She has been at Yale for about 11 years, and what's interesting is that some of her hobbies are that she likes to dance, she likes to travel, and she likes to skydive. So you can ask her about that after the lecture as well. So without further ado, let's welcome Dr. Black to the podium.
Thank you, Anissa. Well, good morning. I have to say good morning also. So today we're going to talk a little bit about having good chemistry, the formation and analysis of compounds. So I work with a couple of different metals, but I figured that everybody recognizes platinum because of the bling bling people, right? Everybody knows platinum. So what is it? It's a metal that's 35 times more rare than gold, and it's used in jewelry, and it's why? Because it's strong and resistant. We have it as a catalytic converter in our cars. In medicine, it can be used for dental stuff, and blood evaluation, and living tissues, and in pacemakers. So we see that that's a multifaceted metal. I have periodic tables for everybody, so if I can have somebody to help give them out. When you look at the periodic table, platinum is number 78. And all this stuff you'll learn later on. But the important part is that all these metals have electrons. And we talk about what are the outermost electrons. Well, in the metal, we have 10 electrons that are outermost, but this D can have 10, and the S can have 2. So we see there's at least one electron that doesn't have a pair. In the complexes I'm going to talk about, here are those 8 electrons, because we had to lose 2. And we'll get to that a little later on. But take note of the color, because the color is important. So there are some cancer drugs that are made with platinum. The earliest one was cisplatin. And here we have platinum. We have 2 groups that we call amines, and we have 2 chlorides from the periodic table. And one of the newer drugs is carboplatinum. Well, a major difference is I can lose these chlorides, but here it will be a little more challenging to lose something to link onto something else. So the drug that I deal with a lot is cisplatin. So it was discovered by Rosenberg, and it's good because it's used for some tumors. So which kind of tumors is it good for? It's good for tumors of cancer of the skin, the bladder, the urethra, ovarian, some lung, some bone, some nasal, and some thyroid. So when you see something that's useful, it also has a bad side. And that bad side is that it's not selective where it targets. So it can give you kidney damage, it can have bone marrow suppression, you can get nausea, it can affect your hearing. So some concerns about that cisplatin drug which arose is that it concentrates in the liver and intestines and kidneys. If you have kidney trouble, you can't use it. If you have bone marrow suppression, you can't use it. And if you're young, it can make you infertile. So people are always trying to design something better. Well, in order to design something better, we have to look at what's there. That's what I like to do, find out what's going on. So that cisplatin, what really does that look like? So can I have 3 volunteers to come up? Okay, come, 1, 2, 3, good. Come up. So you're going to have to take off your Yukon hat for a second. Is that okay? All right. So I'll make you platinum. So why don't you stand out here? You have to stand a little bit more to the front. I'm going to make you an amine. So you hold this shoulder, put this on the shoulder, and hold the other end. And you'll be the other amine on his shoulder. No, this person's shoulder, because he's platinum. He's the important one. So I need you to stick your arm, take your hat. I need you to stick your arms out. So here's the platinum, here's the two amines, and his arms are the two chlorides. Well, why did I not put anybody here? Because these can change. This is the easiest part to pluck off, which is the chlorides. Okay, thank you. I'm going to have to call you back later. So when we bind, we can get up to 4 platinums in a row. And that'll be important a little later on. We'll come back to that. So when I go back, what are these circle things? These circle things are what we call ligands. And so what we need to do is change those circle things. So in the literature, there was a professor from Germany named Bernhard Lippard. And he took this molecule and this one and coupled it or put it together with platinum. So what's the major difference between these two? Is this little thing sticking out here, with it, which is a CH3. So sometimes when we do synthesis, we have to look at what can we change, where can we change it, and what would be the effect. So both of these are 6-membered rings. There was a professor at Harvard, Professor Lippard, and he took this molecule and made a complex. And the one that you saw earlier with 4 platinums, that was a very famous one which he did. Now what's the difference between these two? Well, it's this bond here and this bond here. So one of the ideas I had was, okay, let's see if this thing will bond to the platinum. So you can take what's existing in literature and see if you can modify it to get something better. What's the major difference between these two and the others? Well, I see that now I have a 5-membered ring instead of a 6. And the difference between these is this group right here, which is a CH3. So now I've made a series that's analogous to the 6-membered ring. And here's one of my claim to fame. Nobody had bothered to look at this compound. So it has the same basic structure, the blue, which is where things are going to come together. And I wanted to see, will that have the same kind of reaction as others? We can even get more complicated. And this is true because there are some other complexes which are antibiotics I'll talk about in a little bit, and they have some of the same structure with some changes. So coming back to our original complex, which was 4 platinums in a row. So can I have my 3 original volunteers, and I need 3 more volunteers? Okay. I need 2 more. Come on, come on. Okay, yes. And nobody from the back of the room? 1 person from the back. Come on, 1 more person. Okay, my 3 original volunteers, where are you? You have to take your hat off again. Okay, put your hat back on, and you have to stand to the front. And my other 2, you're going to take your same position. So now we have some new platinum people. You all are platinum, so put these hats on. So now you're going to use one of your hands. You're going to hold one part of this. You're going to hold the other. No, with your other hand. And with this one, you're going to take this. You're going to take that part. So what do we have now? We have 4 platinums in a row. And behind each one of those platinums, we have 2 amines. So now can I have 6 more people? Are there 6 more people who want to come? Whoa, I can't believe people don't want to come. Okay. So you're going to be behind this young lady, and you're going to represent the amines. This guy, I'm sorry. And you're going to act just like that amine, and you're going to be on this person's shoulder. No more? No more? Come. Okay. No, we need 2 on each shoulder. So we need 1 more there and 1 more on this shoulder right here. So we see it's getting kind of crowded here, right? Okay. So what can happen? Well, right now, all those platinums look alike because they all have on the same hat. But what kind of complex I get will depend on what that platinum looks like. So I need you to drop this and you shift that way a little bit. So the first kind of thing we can get, which is called the dimer, it's a dimer because I have 2 platinums and they're bound together. And then I have the amines and stuff on the back of them. So that complex is yellow. So what can happen now? I can get 4 platinums. So shift over, come over. But now she's changed. So that's the second complex. So what does this complex look like? Those 3 platinum are alike, and I have 1 that's different. Well, that complex is going to be blue. And those are there's a whole class of compounds that are like that, which are called platinum blues. What happens if now I change the character of that one, which is the example here? Now, instead of being blue in color, I'm tan in color. And I can go where you're going to break apart. And we have the very last instance, which is the platinum, that complex is red. Okay, let's say thank you to the volunteers, and you may keep your gifts that you have. Welcome. So just like there's a lot of people, it's very crowded in that small space. Well, making those complexes is also, the space is crowded. So my first volunteer 2 arms are these 2 electrons right here. Remember, that's the one that had the chlorides, and that can go away. It has to go away in order to make a complex. So just imagine that I have my 4 platinums. They have their 2 arms out. Uh-oh. Anybody in here play soccer? All right. I got injured. So now I can't use 2 arms. I can only use 1 arm. So that's what this missing space here is. My arm is injured, or that electron has been kicked out. So again, we're coming back to the 2 drugs which we have. And so this is the one that I'm going to talk about a little bit. So once I have that complex, how do I use it with the ligand? Well, first, this is a solid that's yellow. This is a solid that's white. So if I put 2 solids together, unless I do it under high pressure and certain conditions, I'm not going to get a reaction. So I put some water in there, a certain amount, make a certain concentration, and I have to do it in the dark. And when I do, what have I done? I pulled these 2 chlorides off, and I've replaced them with water. I've made this compound, and I know what that is because it settles to the bottom. This is a white compound that just falls out. So I can separate this compound from that one. This is a liquid. This is a solid. I do what we call filtering, and then all I'm interested in is the one that's a liquid. Then I take that, and I add to it whatever the ligand is. So the ligand can be any of those 6-membered, 5-membered, or 4-membered rings. And I make this complex here. What does that look like? It looks like my 4 platinums, but one has a broken arm because I've lost an electron. Well, this complex is yellow. This one is yellow. So I don't know if anything occurred or not. So sometimes we have to add something to get a reaction to go. And we call that thing a catalyst. So the catalyst that's used in this reaction is an acid, nitric acid. When I put that nitric acid in there, let it sit in the cold and the dark, bam, it becomes blue. So I know that I've gotten a reaction to occur. So now that I have that reaction, I have to try to classify what it is. So I take light, which is similar to this laser light, except I measure a certain frequency, and I get this graph. So this graph will tell me what are the major bands, which are the major bondings. So let me have my 4 platinums back up here again. Yes, keep your hats on. So you have to hold one end, she holds the other. Okay? You take one in, you take that one. You can put your other one down. So what's happening here? These two are going to be that little band. These two are going to be that major band because they have a lot more of them around than the other. And that light is exciting them. Okay, you can give me these back. So the light of that UV hitting it is recording some data for me. So that's one piece of data. That data will also, thank you, that data will also help me with my laser. Where should I set my laser light? And I'm going to set it right here at the top of wherever this major band occurs. So if you notice, when I had that broken arm, I have that electron floating around. Well, there's only certain pieces of equipment that can be used to measure that. One of those pieces of equipment is called an EPR machine, electron paramagnetic resonance. This is what it looks like. There's a big magnet. I put my sample down in the magnet. When it goes down, it's going to be aligned in a particular direction. Either my sample is going to be straight up like I am, it's going to be leaning over in one direction, or it's going to be leaning over in another direction. So here I'm the Y, the X, and the Z direction. I'm spinning, and I collect some data. What does that data look like? It looks like this. So I see there's one big major thing that's called G perpendicular, and that has a particular number that goes with it. This part down here is in the parallel region, and that has a particular number that's associated with it. So the nice thing about doing chemistry, PAB is my platinum azotidinone blue. So when you make something new, you get a chance to name it. So that's the nickname for this one. So that gives me a second piece of data. Okay, that proves that I have that broken arm. Another piece of equipment is the FTIR. Well, when I look at this spectra, and that's what we call what we get out, it looks a lot different than this. So in this spectra, when you do it, you have to look at the ligand first by itself. So I have to look at my antibiotic, and here it is. That's what it looks like when I put it in that machine. I put it with the platinum, and this is what I get out. So what's the difference between, do these look alike? No. So I know that something happened, and it happened around in this region, and it happened down in this region, although it could have been wet a little bit. So again, what is this? This is what this equipment looks like. I lift up this chamber. I have to use a certain kind of cell that has to have a certain kind of property. Otherwise, I won't get the good results. I put it in there, hit a couple buttons, I get out this data. Where these bands occur tells me what's going on where, because these are particular to certain complexes. So is this CO? Is it NH? Where is it? And when I see something get blurred or change, that means that that region, that's where that other element is bound. So now here's what I like. This is one of my specialties, which is the laser. This is what the equipment looks like, and here's a close-up of the laser, one type of laser. This happens to be an argon ion tube. That means that I'm taking that argon ion, hitting the sample that is placed in here, is being bounced off, and it gets recorded at another instrument. So what does that spectra look like? Wow, it looks a lot different than the other, because remember, it's in the inverted position like the EPR. So again, here's the azotidinone by itself. And then here's what I get out when I put the platinum there. Well, that's drastically different. So these are platinum NMRs, platinum resonance Ramans. This had no platinum in it, but I can still get the resonance Raman. If there was no making of a compound, this thing would stay the same. But because I made a compound, in this region where I just have this little band of 200, I now see that I have a doublet, 2 bands. In this region where I had about 6 or 7, I now have 2 major ones and a minor one. So it tells me again that yes, I've made what I've been looking for. So that's with the drugs, the 2 drugs. And these reactions have been done with both of these. I just don't have time to show all the data. This thing is called potassium tetrachloroplatinate. I use this to make this compound. So sometimes if something is not pure, I want to see if there's a little, would you get a reaction with this? So I took this precursor, and almost the same kind of way of making it as I did with the other. This compound is red. I put some water in it to make it liquid. I make this complex. This one stays in solution. I add another ligand, and I make a red complex instead of a blue. And so I decided to use that with some antibiotics, because people like to mix what they're using when they're doing drugs sometimes. So we're going to talk about one particular one, which is ampicillin. When I look at ampicillin and I'm talking about the platinum, where can that platinum bind? It can bind between this sulfur and this oxygen. It can bind between this oxygen and that nitrogen, or between this nitrogen, that oxygen, that nitrogen, these 2 oxygens, or this nitrogen and that oxygen. So I have so many different places it can bind. When you first make it, you get all of those. But there are different ratios in which these are made. The trick is to clean it up after you've made it, so that you can see which particular complex you have. So one of the major ways to examine that is using nuclear magnetic resonance. Again, this is what the equipment looks like. And I have a big magnet. So what's the difference? This looks kind of like the EPR one, but it tells me some information about what's going on. So here's the drug, antibiotic by itself. There was no platinum. Well, here it is when I put the platinum in it. So this is with the ampicillin, but it was also done with meslin, which is another antibiotic, piperacil, which is another antibiotic, and penicillin G, which is a very common one. So when I look at the platinum NMRs, I see that platinum NMRs, they're all different. So that tells me something about the complexes that are formed with each one. There are some pieces of the complex that are the same. So this band stays constant. I can now assign that as to what's going on. This band changed shape, but it's still like in this pretty much the same position, and the same thing is occurring here. Another major technique is X-rays. So this is a picture of the X-ray machine. So I put the sample in. Here's a gas cylinder that has to be involved. It has a microscope. So the major difference between this technique and the others, the sample has not only to be a solid, it has to be a crystal. In the EPR, it can be a liquid or a solid, but it doesn't have to be a crystal. It can be a powder. In NMR, it can be a liquid or a solid, and that solid can or cannot be a crystal. In Raman, that sample can be a solid or a liquid or a gas. But that solid does not have to be a crystal. You get the best data when it is. And then you can also do powders with this one. So this one has to be solids that can be powders or crystals. So we see that I made this complex, and it has 4 platinums. So this complex took over a year to make. So what does that mean? It means that I put the 2 things together, I put it in the dark, in the refrigerator after I heated them, and I kept looking at it. Every day at first, then it went to every week, then it went to every month, and then I forgot about it. So I made this one when I was a graduate student. So sometimes when you're a graduate student, your boss will come in and look in the refrigerator and say, "What's that? What's that? What's that?" And it had my name on it. So I was like, "Oh, I forgot about it." Well, when we took it to the X-ray crystallographer, here, this complex that formed. But this complex took a year to form. So it's a very good complex medicinally, but it takes so long to make it that it's not useful. Because you want something that's quick.
What is the goodness of fit in that last slide? What does that represent?
The goodness of fit represents that as I collect that data on several different occasions, and it's several different runs, I should say, how good is the data from each one of those runs? Because this crystal structure was based on all those collections being summed up.
So how well one compares to the other?
How well one compared to the other. So as a scientist, some of the things you need to ask are, what is something that you want to look at? So how did I end up with one of my things being platinum? It's because sometimes you look around, somebody gets sick, they get sicker, and you say, well, what's going on here? People take stuff that they don't necessarily tell the doctor that they took. So you want to see what's going on. So that's how I got into the cisplatin arena. Then when you ask yourself the question, what's going on, then you need to search the literature and say, has somebody else thought about this question? Did they try to answer this question? Did they come up with it? If they didn't, then that's an area that you can work on. And once you decide what you want to look at, then the next thing is to say, how am I going to do this? So one of the ways that you can decide how to do it is to look at what other people have done. Try a tried and true experiment for a different sample. Well, a lot of times that doesn't work. But once you've tried it, you can sit back and think, what can I change? And you systematically change one thing at a time to see what will work. When things do not work, you ask why. And that's sitting back deciding, I need to change this, I need to change that. If it does work, then you say, well, what's the next thing I can pursue? So it's going from those ligands that were shown in the very beginning, which is 6-membered, 5-membered, 4-membered, down to things which are big like the antibiotics, because that's something else that people are taking. But most importantly, whatever it is that you do, you have to love what you do, because then when things don't go right, it doesn't matter. You keep on working on it, because that's very little. It doesn't matter. And nothing works all the time. When you get it to work, it's like, who's your favorite rap artist? Somebody. Who's your favorite rap artist? Do you have a favorite singer, dancer? Yes. What's your name? Courtney. Do you have a favorite singer, dancer? Nobody? You don't have anybody? You have one?
I'm not sure if it's rap. It's Frank Sinatra.
Okay. I wouldn't call him rap, but that feeling when something works. It's like you've gone to a Frank Sinatra concert. He looked at you in the audience and said, come on up stage and follow me for the night. So that's what it's like when something works. I happen to like Ludacris, and Ludacris came on campus. And I happened to get all the way to the very front. And that's why I can say that feeling being up front watching him, trying to get up on the stage and dance, was the same thing as when something works. It works. Your idea was a good one. Your thought process was a good one. So it makes all those times when it didn't work worth it. So we always have to thank people. because you never get to where you are by yourself. First and foremost, I'm going to thank my mom, because if it wasn't for her, I wouldn't be standing here now. This is the person that was my PI, who constantly, he had me thinking I was colorblind. He had me thinking I wasn't working hard enough, but he got me to where I am. This professor met me and invited me to his lab in Germany. And from there, I learned to do things in a much shorter period of time. And this is my other mentors, and here are some students that I've had here. And you can't do your work if you don't have money. So these are some of the people who helped me with the funding of what I'm doing. And so I'd like to say thank you to you as an audience, but also to those who helped me. And does anyone have any questions?